Hi, my name is Annika Hubers,
And I'm Haley Robinson.
and our graduate capstone was an investigation into ultra-low frequency auditory brainstem responses in human subjects. So our objective in this study was to investigate ultra-low frequency auditory brainstem responses in a normal hearing population. So ABR responses using frequencies below 500 hertz have not been well studied, and their clinical significance is unknown. This is mainly due to limitations in technology and the thought that these ultra-low frequencies hold minimal importance for speech understanding. Ultimately, we want to identify potential normative ultra-low frequency ABR responses in normal hearing subjects. So some background information that's helpful. Advancements in clinical equipment have enabled researchers to begin evaluating the extreme ends of the frequency spectrum. Standard clinical equipment now allows use of ultra-high frequency headphones, assessment through otoacoustic emissions testing, and creation of special stimuli in evoked potentials, tone bursts and chirps, to assess these areas, although these are primarily limited to the extended high frequency range. Research and clinical availability continue to be limited for the ultra-low frequency sounds. The auditory brainstem response, or ABR, is a routine clinical assessment and research tool. Daily newborn infant hearing screenings are conducted by automated ABRs, assisting in the early identification of hearing loss. An ABR is like an EEG. It uses skin electrodes placed on either ear and a third on the forehead, and a sound stimulus is placed into the ear and waveforms are elicited from a healthy auditory nerve. The typical ABR is obtained using click or tone burst stimuli. Click stimuli have a center frequency or spectral energy that is around 4,000 hertz, and tone burst stimuli can allow for more frequency-specific information to be obtained. They're typically within somewhere around 500 to 4,000 hertz. There is an abundance of literature regarding click and tone burst auditory brainstem responses and their clinical applications, but there is still very little known about frequencies under 500 hertz. When reading the output of an ABR waveform, audiologists typically identify three significant waves. That would be waves 1, 3, and 5, often indicated with Roman numerals at specific time domains. So we can kind of identify where certain waves should be happening. Normative data shows that higher frequency stimuli, a click or stimuli over 2,000 hertz, typically result in shorter latencies of the ABR waveform because of good neural synchrony. Clicks are broadband stimuli and thus excite a wider range of the cochlea. Morphology and latency details of a low frequency or below 500 hertz ABR waveform are relatively unknown.
So, to address some of the gaps in the research, there has been a historical focus on the traditional audiogram that evaluates speech frequencies, which are 250 to 8,000 hertz. However, the human range of audibility spans from 20 to 20,000 hertz, leaving a large portion of the human audibility spectrum unstudied and untested. Until recently, there was minimal thought that the ultra-high frequencies, or greater than 8,000 hertz, had any impact on speech intelligibility. However, new research is emerging demonstrating that these frequencies do in fact impact speech understanding. Due to advance in technologies, these lesser known and lesser studied frequencies are receiving more attention. Researchers have used ultra-high frequency headphones, otoacoustic emissions, and special stimuli in evoked potentials, like the tone bursts and chirps, to assess these areas. Ultra-low frequency stimuli require more energy to produce as the wavelength is longer. This means to produce the stimuli, a large speaker is needed. Due to equipment limitations, these ultra-low frequencies cannot be delivered via traditional ABR transducers, nor are the stimuli developed for clinical equipment yet. So the possible utility of our study is the low frequency ABRs remain unknown without any exploration. Whether this type of test could be used in audiology test battery or differential diagnosis requires more research. So the first step to address this is to compare the ultra-low frequency ABRs to our standard use ABRs. Using a speaker with subsonic capabilities, ultra-low frequencies can be evaluated. The study aims to assess ABRs elicited by ultra-low frequency stimuli like 30 Hz compared to ABRs elicited by standard stimuli like the click or 500 Hz tone burst in humans with normal hearing sensitivity. Once we understand morphology and latency in ultra-low frequencies, then researchers can begin to develop normative data and evaluate any potential impact on speech understanding.
So we have two main hypotheses. The first is that the wave 5 of our 30 Hz tone burst ABR will have a longer latency than the wave 5 of the click stimuli ABR. Our second hypothesis, very similar, wave 5 of that 30 Hz tone burst ABR will have a longer latency than the wave 5 of the 500 Hz tone burst ABR. We can hypothesize that these waveform latencies would be longer as low frequencies are arranged at the apical end of the cochlea, and the eliciting 30 Hz stimuli would take longer to reach the frequency-specific sensory hair cells of the inner ear. As the traveling wave moves towards the apex, the velocity of the traveling wave decreases. This results in less neural synchrony in the apical parts of the cochlea and therefore poorer morphology of waveforms. We can see the start of this reduced morphology in the 500 Hz tone burst ABR, especially when compared to clicks. So, when conducting this study, each of the participants was seated comfortably in a chair for the duration of the test. We used intelligent hearing systems equipment for testing. The inverting and non-inverting electrode montage was also used. This electrode array consists of 3 electrodes placed on the participant. Inverting sticker electrodes are placed on the left earlobe and right earlobe, and a midline non-inverting electrode is placed on the high forehead. Stimuli was presented suprathreshold, and we obtained, at minimum, 2 repeatable traces for each of the stimuli. Waves 1, 3, and 5 were recorded and identified when possible, and 3 different stimuli were tested: that click, the 500 Hz tone burst, and the 30 Hz tone burst. The ABR waveform data was recorded from the left ear only with binaural presentation of the stimulus. This is due to the fact that obtaining the 30 Hz signal is done through a seismic speaker, and isolation of one ear is not possible. Therefore, the stimulus presentation was binaural, or presented to both ears for all 3 stimuli. Foam earplugs were placed in each of the participants' ears, and that binaural stimulus, either the click or tone burst, was presented through those ear inserts. The output was then recorded. The click stimulus was recorded first, followed by the 500 Hz tone burst, and again, at minimum, 2 runs per stimulus were collected. For the 30 Hz tone burst, the subject was seated in front of the seismic speaker, and a minimum of 2 runs were recorded.
So from this chart, you can see the ABR testing and stimulus parameters that were used. The most notable things to point out are that a faster rate was used for the click stimulus versus the 2 lower tone bursts for the 500 Hz and 30 Hz stimulus, and also that the time window was lengthened for the 500 Hz and 30 Hz stimulus, given that we know that it's going to be a longer waveform.
Here we have some of the data we collected. We have a couple that we'll show, but overall it reflects the general theme of our findings. Here at the top, you can see one participant's waveforms for the click stimulus ABR. The peaks are labeled 1, 3, and 5. There is repeatability there. Then we have the 500 Hz tone burst. We were able to label wave 3 and wave 5. There was repeatability and there were identifiable peaks in these, but if you look here, this is these are all 3 waves from that 30 Hz tone burst. We did not see any identifiable peaks or anything that could be labeled definitively, nor was there much repeatability in these waveforms, which is what you look for. So overall, this yielded nothing usable in that 30 hertz ABR. Again, we have the click stimulus elicited ABR waveform with 1, 3, and 5 labeled, as well as the 500 hertz tone burst with 3 and 5 identified. And over here again in blue was the 30 hertz tone burst ABR. There was no repeatability, no identifiable peaks, and overall nothing definitive that could be identified or labeled. Third example here, nice repeatable waveform for the click with peaks 1, 3, and 5. We have that 500 hertz tone burst with wave 5 right there. And then the 3 tracings of this participant's 30 hertz tone burst with no repeatable peaks and nothing identifiable there.
So, interpreting our results, there was no identifiable normative responses observed in the waveform output of the 30 Hz ABR for any test subject, and no identifiable peak latency responses were observed in the waveform output for the 30 Hz ABR, again, for any of the test subjects participating.
When looking at the lack of identifiable peaks or repeatability in those 30 Hz tone burst elicited ABRs, we had a number of considerations during the data collection process. First was that a longer recording window could have been beneficial in identifying some later components of the waveform that might have just existed outside of that 25 millisecond recording window that we used. We also considered that maybe neural fatigue of the participants led to decreased neural synchrony. So in the future, potentially using or allowing participants to have a considerable amount of time between each of the 3 stimuli and also between each of the recordings that were done might allow their nerves to rest and decrease that amount of neural fatigue, increasing the neural synchrony. It was also a bit difficult in the testing process to completely eliminate any vibrations that were caused by the output of that seismic speaker when presenting the 30 Hz tone burst. So if there could be a more empty, isolated area available for testing, that might have allowed for increased neural synchrony, as the vibrations could have potentially impacted the repeatability of those waveforms.
In conclusion, further research may yield more applicable findings, and additional studies with larger subject groups may reveal more normative data. Also, resolving any previously mentioned considerations may yield repeatable responses that could have contributed to normative data as well.
Thank you.